Hello everyone. As all of you know that in our last class we started with the traditional approach to derive IV characteristics of the MOSFET, and as most of you would know that the traditional approach is centered around long channel MOSFETs. That was done by keeping long channel MOSFETs in mind. And so just for the sake of completion of the treatment of MOSFET, we will also go through the traditional approach to derive IV characteristics of the MOSFET, although we have seen that in the small channel MOSFETs that approach is no longer applicable because the Roots model of conduction is no longer applicable in the small channel MOSFETs. But still we would go through the traditional approach just for the sake of completion of this MOSFET treatment. Before going into that, let me quickly review what we have seen. This is what we have seen so far. The MOSFET geometry is this is the physical form of the MOSFET geometry, and in the energy landscape this geometry actually gives us a barrier in the channel, and this barrier can be controlled by the gate voltage primarily. Also this not the barrier but this landscape of the energy electronic energy can be changed by the drain voltage as well. So the effect of the gate voltage is shown in this figure and the effect of the drain voltage is shown in this figure. Okay. The general form of IV characteristics is written in this way, and this is true for any device. I would say that the current depends on the charge available for conduction times the velocity at which the charge will move times the width of the device. Okay. And what we have seen is that the MOSFET IV characteristics generally broken down in two parts. One is the output characteristics, that is the relationship between IDS and VDS, and second is the transfer characteristics, which is the relationship between IDS and VGS. So the output characteristics has a linear regime, a saturation regime, and also a subthreshold regime. This subthreshold regime is more clearly, I would say, present in the transfer characteristics, which is basically IDS versus VGS relationship, and the plot for VGS less than VT values is the subthreshold regime. And if we instead of plotting IDS versus VGS, if we plot log IDS, logarithmic function of IDS, this will give us a better a zoomed in picture of the current in this regime, and this is how the current will look like when we have log 10 IDS on the y axis, and if we plot it as a function of VGS which is there on the x axis. On this we can see that we come across a new MOSFET parameter which is known as the subthreshold swing, which is the inverse of the slope of this curve, and this tells us about how much control does the gate has on the channel. So if the subthreshold swing is less, it means that the gate has more control over the channel, and if the subthreshold swing is more, it means that the gate has less control on the channel. The unit of the subthreshold swing is millivolt per decade. So it is essentially the amount of gate voltage that is required to change the channel current by a factor of 10. Okay. In this we also saw the effect of drain voltage on the IV characteristics, especially for small devices, and in the small devices the barrier is no longer shielded from the drain terminal electrostatically because now the channel length is extremely small, and if we apply a voltage on the drain terminal, it will reduce the barrier in the channel, and this is known as the drain induced barrier lowering, and this reflects in shifting of the curve to the left side for high drain voltages. So if drain voltage is less 0.05 volts, the IV curve is on the right side. If the drain voltage is high, VDS is equal to VDD, the drain voltage is shifted to the left side. This is the DIBL. Ideally, we would not like DIBL to be present in our devices. Now, let us quickly come back to the traditional treatment of IV characteristics. Generally, it is assumed that in a MOSFET, when the gate voltage VGS is less than the threshold voltage, in that case the channel charge is negligible or it is extremely small, tends to 0, and the charge appears only when the gate voltage is greater than or equal to the threshold voltage. Okay. So, what is a better starting point than the general expression for the current? In this, in the general expression of current, we need the charge and we need the velocity with which the charge moves. The charge can be derived from the, by assuming that, or by from the capacitance approximation of the gate channel, this part of the device. So, this part of the MOSFET can be approximated by a capacitor because we have a conducting gate plate, conducting gate contact, we have a conducting channel, and in between we have an insulator or the dielectric. So, if the capacitance of this capacitor is Cg, the gate capacitance of the MOSFET, which is approximately equal to Cox in most of the cases. So, generally, while we do not want to deal with the details of the capacitance in the MOSFET, we generally take Cg to be equal to Cox, but ideally Cg includes Cox and the depletion capacitance of the channel. So, if we have this if we have a capacitor with capacitance Cg or Cox, let us say, and we know the voltage applied across it, we can easily deduce the charge that appears on the plates of the capacitor. So, the charge in the channel can be written as to be minus Cox, because we are applying a positive voltage on the gate side. So, the charge that will appear on the channel side will be negative VGS minus VT, because charge only appears when the gate voltage is above the threshold voltage. So, the voltage that contributes in producing charge in the channel is the voltage in excess to the threshold voltage, which means VGS minus VT. So, the charge in the channel when the source and the drain terminal are grounded, in that case the charge is given as minus Cox times VGS minus VT, where Cox is essentially the capacitance of this gate oxide, and it is written as Kox times epsilon naught divided by Tox, where in the numerator this is the dielectric constant of the insulator and this is the oxide thickness. This is basically this direction, this is the Tox, thickness of oxide on top of the channel. So, so there are two regimes of operation broadly. One is the linear regime, which means the VDS, is small in the linear regime. Okay. So, in the linear regime, what would be the velocity of the charge carriers? So, the velocity will be from this basic relationship, the velocity of electrons, because this is the channel consists of electrons, this will be directly dependent on the mobility of electrons and the electric field. Okay. So, the average velocity will be let us write it as average electric field. And for in the linear regime, when VDS is small, the electric field can be written as, if the channel length is L, as we have seen earlier that in the linear regime when VDS is small, in that case the electric field is almost constant because VDS varies linearly, the drop of voltage is linear in the channel. So, this can be written as minus VDS by L. So, it can be assumed that this voltage VDS drops uniformly across the channel. So, on one side of the channel, on the source side, we have the 0 volts applied, on the drain side we have VDS volts applied, and in the linear regime it is assumed that this voltage drops uniformly. So, the electric field is generally minus VDS by L. This can be taken as like this. So, we know the charge, we know the velocity. So, in this case we can easily find out the current. So, now the current from the general expression of the current IDS is essentially W times minus C aux. So, this minus W times minus C aux VGS minus VT times minus mu n VDS by L. So, this turns out to be mu n C aux VGS minus VT into VDS times W by L. So, this is the traditionally how the current is derived in the MOSFET. This is the expression of current in the linear regime. So, we are at the moment we are looking at how the current would be there in the linear regime and in the saturation regime. Finally, we will also see a more general expression of the current. So, in the linear regime, as you can see, IDS is directly proportional to VDS and IDS is directly proportional to VGS minus VT. Okay. So, in the linear regime, the current varies linearly with the drain voltage. That is why this name is there, that is why this regime is known as the linear regime. Okay. So, that is true. So, this expression is only true for small biases when the VDS is very small. In the saturation regime, when VDS is no longer small, and we have seen while discussing the output characteristics IDS versus VDS that this regime is known as the saturation regime. And we have also discussed that there could be two reasons for this saturation. One is in the small channel MOSFETs, this might be because of the velocity saturation, and in the long channel MOSFET, this could be because of the pinch off in the channel. Because in long channel MOSFET, if we apply high drain voltage, the difference between the gate terminal, the voltage difference between the gate terminal and the drain side of the channel is small, and the channel is pinched off from the drain side, and that is essentially responsible for the saturation in the current. So, let us consider the case of velocity saturation. So, as we have seen that, and this happens in small channel MOSFETs, because when the channel length is very small, the electric field becomes extremely high and the velocity actually saturates to a certain value. So, in one of our previous discussions, we have seen that typically an electric field of around 10 kilovolt per centimeter is required to saturate the velocity in bulk silicon. And if we have, let us say, a 20 nanometer MOSFET or even 50 nanometer MOSFET, and if we apply a source voltage a drain to source voltage to be of 1 volt, the electric field will be way higher than this value. So, the velocity would possibly saturate given there is enough scattering in the channel. Okay. So, generally the velocity saturates to this value. So, the Vx this term becomes the Vsat, which is typically centimeter 10 to the power 7 centimeter per second. So, in this case the current, we just need to put this Qn and this velocity. So, that this IDS essentially becomes W times Cox times Vsat into Vgs minus Vt. Okay. This velocity is generally taken to be negative because the current, the direction of the current and the direction of electrons is in opposite direction. So, that is why this negative sign goes away. And as you can see that this IDS is independent of, from this IDS is independent of VDS. So, that is the case when the saturation is taking place because of the velocity saturation in small channel MOSFETs. Okay. Generally, this this velocity saturation model that is used when the channel length is smaller than 1 micrometer, because in that case the electric field becomes higher than this value. Okay. Now, let us consider the case of classical pinch off. Classical pinch off means that we have a long channel, but because of the high drain voltage the channel is getting pinched off from the drain side. So, in this case, so this barrier shape will be, and this happens at high VDS. So, for higher VDS, as we have also discussed previously, that the electric field will be non-linear in the channel, especially in this part. On one side the electric field will be extremely low, especially on the top of the barrier, but it will very quickly become, it will very quickly drop abruptly just to the right of the top of the barrier, and it is a non-linearly changing electric field. So, in this case the charge we need to take, so in addition to the effect of the gate voltage on the channel, we also need to consider the effect of the drain voltage on the channel, because now high VDS is there. So, this channel charge will be minus Cox Vgs minus Vt minus Vx, where this Vx is the voltage due to the drain voltage. Okay. And this will change across the channel. On the source side this will be 0, on the drain side this will be VDD, and in between it will be an arbitrary value Vx. So, this will be the charge, and what would be the velocity? The velocity will be from this, the velocity will be derived in long channel MOSFET using this. The electric field, because now the barrier is because the electric field in the barrier is non-linear, so on one side the voltage is 0, on other side the voltage is VDD, and in between the voltage is changing non-linearly. So, this electric field is actually written as Vgs minus Vt divided by 2 L prime. This is after considering all kind of non-linearities in the channel. Okay. We will see where this comes from as well, but just assume that just in the beginning, right at the beginning of the channel, this is the electric field. So, in this case the velocity can be written as minus mu n times this electric field, the charge is this. So, the current from this expression, from the general expression of the current, from this expression, the current in the saturation regime can be written as IDS is equal to W by 2L prime now times mu n Cox VGS minus VT minus Vx VGS minus VT. Okay. And since we are considering the velocity just at the beginning of the channel, so this Vx will be 0 at that point. So, this can be removed from here. And finally, Vgs minus Vt times Vgs minus Vt becomes Vgs minus Vt square. So, what we will eventually have is Vgs minus Vt square. So, this will be the current in the saturation regime because of the classical pinch off. We haven't shown where this comes from actually, but this is just to show you various extremes of IV characteristics. In linear regime, electric field is constant because the voltage drop is assumed to be linear. The charge is just because of the gate voltage, so the current can be easily deduced using these two expressions, these three expressions, from this general expression, this current expression and the velocity expression. In the saturation regime, when the velocity is getting saturated because of the when the current is getting saturated because of the velocity saturation, which is the case for small channels, in that case this Vx is taken to be the saturated velocity and Qn is taken to be the charge because of the gate voltage. In the classical pinch off, in addition to the effect of gate voltage on the charge, we also need to take the effect of the drain voltage, and the velocity will be calculated from the electric field. Electric field is given by this value, and from here we derive the current. In a more general way, this current is given as W times Qnx. So, this is the general treatment of the IV characteristics times the velocity. Okay. So, this in a very general sense, this Qn can be written as minus Cox into Vgs minus Vt minus Vx, where Vx is the voltage because of the drain voltage now. And this Vx can be written as minus mu n times electric field, where electric field this mu n times electric field, and electric field is minus dV by dx. This is the gradient of the voltage in the channel. So, this general expression of the current can be written as, by multiplying these two equations, mu n Cox to W Vgs minus Vt minus Vx times dV by dx. Okay. So, this dx can be brought to the left side, Ids times dx is equal to mu n Cox W Vgs minus Vt minus Vx times dV. Okay. So, if we integrate this equation across the channel, So, from 0 to L, on the right side the voltage will vary from Vs to Vd. So, this will give us IDS is times L is equal to W times mu n Cox VGS minus Vt times V, which into VDS minus VDS square by 2. So, this voltage will also be from Vs to Vd, Vs is equal to 0, Vd is equal to VDS. So, this is the general expression of the current. This L can be taken to the right hand side, and in that case it will become W by L. So, this is classically, traditionally the way IV characteristics of the MOSFET is derived. There is a small point here which I would just like to highlight, that in a MOSFET we have a source, we have a drain, and because of the drain voltage the channel might be pinched off. So, the channel will terminate at a length, let us say L prime. The total length is L, let us say this is L, but the channel will terminate at L prime because of the, this is L, this is L prime. The channel will terminate at L prime because of the drain voltage. Okay. So, in this case the voltage here is VGS minus VT, the drain voltage here is VGS minus VT. And if we integrate this equation from 0 to L prime only, this will be IDS times IDS will be equal to W by L prime. On the right hand side the limits will be from 0 to VGS minus VT. So, it will be mu n Cox, VDS needs to be put as VGS minus VT. So, it will be VGS minus VT square minus, so it will be VGS minus VT square by 2, and 2 can come here. So, this shows the saturation of the current in the channel, that the current has become independent of the drain voltage in the channel. Okay. So, this is classically the way the current is typically derived, as is also seen here. In the previous slide we considered the extreme case. We derived the current when we take the linear regime just or the saturation regime. Now, there is another thing, important analysis that we need to do, that generally is done, that is the electric field versus position in the channel, electric field as a function of the position in the channel. So, generally we would like to know the electric field profile in the saturation regime, because it is highly nonlinear profile. In linear regime, as we have discussed, typically it is a linear one, but quantitatively or precisely how does it look like, that is what we will see now. And we will take help from the current expression. So, this is the general form of the current expression. IDS is equal to W by L mu n Cox VGS minus VT VDS minus VDS square by 2. At an arbitrary point in the channel, so this current is always constant, uniform through the channel in steady state. So, this is the current that we derived previously, but at any arbitrary point in the channel, let us say at x, VDS will be Vx, and the current at any arbitrary point will be W times mu n Cox VGS minus VT minus Vx times dV by dx. So, this will be the current at any arbitrary point in the channel. So, if we equate this current with this arbitrary current, Ideally they should be the same, because in steady state the current is uniform, the current is the same all across the channel. So by equating this expression to this expression, we obtain this, and by having a change of variables on both sides, if we bring dx on the left side, so on the left side it becomes dx by L prime. This will, so if this is brought to the left side, it will be dx by L prime, and if we integrate this thing now from 0 to x at any point x. So on the left side what will be there is Vgs minus Vt times Vds minus Vds square by 2 times x by L prime. On the right side we will have Vgs minus Vt, the integration is with respect to voltage. Vgs minus Vt, it will be from 0 to Vx times Vx minus Vx square by 2. So now this becomes a quadratic equation in the voltage across the channel. So it is a quadratic equation, Vx square by 2 minus Vx times Vgs minus Vt plus Vgs minus Vt times Vds minus Vds x by L 0. So this becomes an equation like this: ax square plus bx plus c is equal to 0. And as all of us know from the basic maths, we can solve this quadratic equation, and that's what your homework assignment is now. So you need to solve this quadratic equation as a function of Vx, and then minus del Vx by del x will give us the electric field at any arbitrary point in the channel. So that's how this electric field is calculated at any arbitrary point in the channel in the traditional MOSFET theory. So please go through this and try solving this quadratic equation in voltage and try to see how this Ex looks like. Calculation might become slightly tedious, but it's not a it's a doable calculation, so just give it an attempt. Okay, so we'll discuss this point onwards in the next class. I thank you for your attention. See you in the next class.